Hello everyone and welcome to another video. In today's video we are going to finally define the derivative. So what is the derivative? The derivative is a function, okay? It is a function whose y value is the slope of the tangent for any value of its original function. So really the key here is that the derivative is in itself a function. And the y value is going to be the slope of the tangent at the given x value, okay? So this is similar to what we have done before, but now our answer will be an expression and not just a value. So in the previous unit, we were finding the derivative at a specific point. So we were finding a specific y value, which is the slope of the tangent at that point. Now, in this unit, we are going to learn how to determine the general expression to find the function of the derivative, okay? And in order to do that, we need to use a formula which is known as first principles. And this is where the formal definition of the derivative comes from, okay? Using first principles. And first principles states that the limit as h approaches 0 of f of x plus h minus f of x over h is equal to the derivative function, okay? So where is this coming from? Again, this goes back to the definition that we learned in Unit 1, right? This goes back to the definition of slope. Previously, we have seen that the formula for the slope is given by y2 minus y1 over x2 minus x1, or the difference in y over the difference in x. If we have 2 points on a curve, right? Where point 1, it has coordinates x1, y1, and point 2 has coordinates x2, y2. In this case, we want to find the derivative function. And so we are going to take the limit, instead of using the old slope formula, we are going to use the first principles formula, which we have seen before. And we are going to we're not going to plug in a specific value for x, which is what we have done previously. We are going to just use the function as is, and we are going to take the limit as h goes to 0, okay? So let's take a look at a couple of examples here. Use first principles to find the derivative if the function given is x cubed plus 3x squared minus 4. So again, let's start by stating the definition of the derivative using first principles. So we are going to have f of x plus h minus f of x all over h. And of course, we cannot forget that we need to take the limit of that full expression. That's where the magic happens, because we're taking the limit as h approaches 0, okay? So keeping up with our notation now, we are going to plug in the values that we are given. So instead of just having x, we are going to apply the function to our input here, which is going to be x plus h. So instead of x, I am going to have x plus h cubed plus 3. Instead of x, I'm going to have x plus h squared minus 4, and now minus just f of x as it is, right? So minus x cubed plus 3x squared minus 4. And this, of course, all over h. And yes, it is going to be a big expression that now we are going to expand and simplify. Okay? So now here we are going to have the limit as h approaches 0. Let's expand x plus h to the power of 3. So this is a cubic expression, right? So remember, we can use Pascal's triangle, or maybe you have just memorized how this expansion happens. And if so, whichever case, however you want to do it, whatever works for you. But here we are going to have x to the power of 3 plus 3 x squared h plus 3x h squared plus h cubed. And now, so this is the expansion of x plus h cubed, right? And now let's expand plus 3 x squared plus 2xh plus h squared. So now that is going to be the expansion of the middle term there, right? And then minus 4, and of course all of this minus x cubed minus 3x squared and plus 4. And immediately here, I see that I am able to cancel a few things already, right? I see that I'm going to be able to cancel out the x cubes and the 4s because I have both a positive and a negative copy of each. And with that, we keep simplifying. This, of course, all over h. Okay, so the h is just staying there in the denominator for now. We'll see what happens to it in a few steps. So there we go. Let's now simplify even more. So here we are going to have 3x squared h plus 3x h squared plus h cubed. And now I'm going to distribute this 3 here. So I'm going to have plus 3x squared plus 6xh plus 3h squared. And now minus 3x squared. And here again, I see that I can further cancel the positive 3x squared with the negative 3x squared to get the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed plus 6xh plus 3h squared all over h. And now what we notice is that each term in the numerator has a factor of h. So I'm going to factor that out to cancel with the h in the denominator, okay, which is going to effectively cancel the h in the denominator, and then I'm going to be able to evaluate my limit. So let's do that. Limit as h approaches 0 of 3x squared. So I'm factoring out that h, right? So I'm going to have 3x squared plus 3xh plus h squared plus 6x plus 3h all over h. So now the h that we factored out will cancel out with the h in the denominator. And I am going to be left with the limit as h approaches 0 of 3x squared plus 3xh plus h squared plus 6x plus 3h. And so now this is where I can directly evaluate the limit. And so I am going to have 3x squared plus 3x times 0, because in order to evaluate the limit, I am just going to plug in 0 for h, plus 0 squared plus 6h plus 3 times 0. And now, of course, all of these terms that are being multiplied by 0 go away. And I am going to be left with the final expression, 3x squared plus 6h. Okay, and so this is our derivative, all right? The derivative of x to the power of 3 plus 3x to the power of 2 minus 4 is equal to 3x squared plus 6x. Okay? That is our final answer. Let's take a look at another example. What if we have a square root expression? What if we have a function with a square root? So here, this is where we are going to have to use different skills, and this is where we are going to use rationalization. Okay, but again, let's see how it works step by step. We are going to start by setting it up. So here again, going back to that definition of the derivative, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. All right, so this is going to be equal to the limit. So now instead of having x plus h, I'm going to actually substitute in the value of the function. Okay, so the limit as h approaches 0. So here, instead of x, I am going to have x plus h, right? So I am going to have f of x plus h is equal to the square root of 3 x plus h minus 4 plus 1. So all I'm doing is replacing the x values with x plus h. Okay, so I'm going to have the limit as h approaches 0 of 3 x plus h plus 4, or sorry, minus 4 plus 1. The plus 1 outside of the square root. And now minus, so here this is where I'm going to subtract the original f of x. So minus the square root of 3x minus 4 plus 1. And this all over h, just like before. Okay. All right. So let's expand here and simplify. Let's see where that gets us. And so here we are going to have 3x plus 3h minus 4 plus 1 minus the square root of 3x minus 4 minus 1 after I distribute that negative sign, right? All over h. Okay, so here clearly I can cancel out the positive with the negative 1. And I am going to be left with the square root of 3x plus 3h minus 4 minus the square root of 3x minus 4, and all of this over h. All right, and so now here I cannot go any further. I have expanded and simplified as much as I can. So I need a different method now to continuing evaluate the limit. And this is where I need to rationalize the numerator, right? I need to be able to rewrite this expression without the square roots in order for me to be able to further simplify. So again, let's recall, how do we rationalize either a numerator or a denominator? We need the conjugate. So we need to multiply both the numerator and the denominator by the conjugate. Okay, so let's do that. The limit as h approaches 0, I'm just going to rewrite the expression as it was. 3x plus 3h minus 4 minus square root of 3x minus 4 all over h. And so now here I'm going to multiply both the numerator and the denominator by the conjugate. And the conjugate of this expression, right, if this is term A and right here we have term B, then the only thing that we are changing is that minus sign there in between those terms. So I'm going to have the square root of 3x plus 3h minus 4. None of the signs there are changing. The only sign that changes is that sign in the middle. It's going to change from a minus to a plus. So plus the square root of 3x minus 4. And now I have to divide by the exact same amount because I do not want to alter the value of the expression, right? Multiplying and dividing by the same amount is the same as multiplying by 1. So really I am not affecting the final value of the expression because I'm just multiplying by 1. All right, so now let's simplify all of this. For the numerator, we are going to end up with the square root of 3x plus 3h minus 4 times the square root of 3x plus 3h minus 4, right? We have basically here, we have a difference of squares, right? That make up our numerator. So we can just take the square of the first term, which is going to be equal to 3x plus 3h minus 4, and now minus, and we are going to take the square of the second term, which is going to be 3x minus 4. And that is going to be our new numerator. For our denominator, well, we are going to have h times this whole expression here. All right, so h times the square root of 3x plus 3h minus 4 plus the square root of 3x minus 4. So now I can simplify. Here, instead of having minus 3x minus 4, I can simplify this to 3x plus 3h minus 4 minus 3x plus 4 all over the same denominator. And now I see that there's a couple of things here that I can cancel out. I can cancel out the 3x with the negative 3x. I can cancel out the negative 4 with the positive 4. And then I am going to be left with the limit as h approaches 0 of 3h over h, square root of 3x plus 3h minus 4 plus the square root of 3x minus 4 in the denominator. And here again, I am able to cancel out the h in the numerator and the h in the denominator to get to a final expression, the limit of 3 over the square root of 3x plus 3h minus 4 plus the square root of 3x minus 4. And so here now, I have cancelled out the h in the denominator that would have led to an undefined form. And so I am able to directly evaluate the limit now. And to do that, again, I am going to sub in h is equal to 0 into this final expression. And that is going to give me 3 over the square root of 3x plus 3 times 0 minus 4 plus the square root of 3x minus 4. This is going to be equal to 3 over the square root of 3x minus 4 plus the square root of 3x minus 4, which I am just going to rewrite as 3 over 2 square root of 3x minus 4. And so this is the derivative of the function that we were given. This is the derivative of f of x is equal to 3x minus 4 plus 1. So here again, f prime of x is equal to 3 over 2 square root of 3x minus 4. So that is the final derivative, which is a function in and of itself, right? All right, so we have seen a couple of different functions, right? We saw a polynomial, we saw a square root function. So are all functions differentiable? No, they're not all differentiable, okay? So we do have some rules for differentiability, okay? We do have some rules for differentiability because not all functions are differentiable. All right, so what are those rules? Well, in order to find a derivative, you must have a non-vertical unique tangent, okay? A non-vertical unique tangent. So graphically, the curve will be smooth and continuous. This means that we cannot have any corners, all right? No corners. So for example, the absolute value function, it is not differentiable, okay? Because we do have a sharp corner when x is equal to 0. We also cannot have any cusps, and we can have any discontinuities, okay? So that means no holes, no jumps, and no asymptotes. Okay. No holes, no jumps, no asymptotes. If we have any of these in the graph of the function, then that means that the function is not differentiable, or it might only be differentiable in certain intervals. Okay. A final note before we end the video is on notation. You might have noticed that in this video I am mostly, or really for all of the video, I have used prime notation. Okay, f prime of x, that was a notation that I have used this entire video. So this is what we call prime notation. And we can just interchange f of x with y. So you might also see y prime being used for f of x. That is also perfectly fine. And the way that we represent prime notation is with an apostrophe. Okay, that little line that goes right there in between f of x, or that goes right next to y, that is what we call an apostrophe. And so that is the notation for prime notation. If you are watching other videos or even your textbook, other sources, what you might see is a different kind of notation, which is given by dy over dx. So this notation is known as Leibniz notation. Leibniz was a very famous mathematician who is considered to be one of the founding fathers of calculus, along with Isaac Newton. He is thought to have put forth this notation of dy over dx. And so this notation is also used a lot in physics and engineering, because it explicitly denotes the derivative as a rate of change, okay? Indicates that the derivative is a rate of change. So we know that the derivative gives us the instantaneous rate of change of a function at a specific point, right? But the function as a whole, it basically gives us the change in y with respect to the change in x, right? So it tells us, as x is changing, how is y changing? So the derivative gives us the change in y with respect to the change in x. All right, so basically, when we write dy over dx, this is equivalent to writing delta y over delta x, where of course delta, that little triangle, represents the change in y over the change in x, which is also where the formula for the slope comes from. So again, here we have gone full circle. All right, everyone, I hope that this video was useful, and I will see you in the next one. Bye.